Alright, so for the last magnetic moment, we'll talk about the magnetic moment that we usually talk about in physics, which is the magnetic moment of a current loop. So those other ones are materials. I have a soft spot for materials myself, but in the books they don't normally talk about these current loops, which is strange because everybody wants to talk about how cool magnets are, and then they talk about current loops and stuff like that, and nobody really understands why. This is because basically all, at some level at least, all magnetic moments are current loops. So this is in contradistinction, remember, to the electric dipole moment instead of the magnetic dipole moment, which had charges on either side. But sometimes it's going to be useful to pretend that your dipole is a physical dipole like this rather than a current dipole. So what we'll do here is we will first calculate the magnetic moment for this loop, and then we'll pretend like it's a 10 centimeter distance between these two poles, and we'll calculate what the pole strength would be if there was such a thing as a magnetic pole. But there is no such thing, but it's a thing that we can use to help us. It's a fiction we can use to help us do some calculations, especially things like forces on these dipoles. In fact, if you don't have calculus and you want to do forces on magnetic moments, you need to do something like this. All right. And we don't use calculus in this class. So let's see, what is the magnetic moment? Well, the basic idea of magnetic moment is the current times the area. You might get that from the units that we've been using. So the magnetic moment had amps per meters, or amps times meters squared, as its units. Strangely enough, that means if you take a current and you multiply it by an area, you get a magnetic moment. So if I have a 1 amp current, multiply it by the area of this square, which is 1 centimeter by 1 centimeter, so that's 0.1 meters squared. Oh, it's 1 centimeter, 0.01, excuse me. All right. Then, let's see, we have 1 times 10 to the minus 4 amps meters squared, which could also be 100 microamps times meters squared. Okay, so that's the magnetic moment there. Good, we're okay with that one. Now I want to figure out what the charges on this would be if we had this moment that we just calculated, m, for this guy. So remember, this is an analogy between magnetism and electricity. So the electric dipole moment was P equals QD. And so M is going to be so that's your electric dipole moment. Your magnetic dipole moment is going to be QM, this imaginary magnetic charge, times the distance between the charges. We said here it was 10 centimeters. So that means QM is equal to, this is too far down, M over D. We said M was 100 microamp meters squared. And then we said D was 10 centimeters, 0.1 meters. So that gives us 1 milliamp times a meter, 1 milliamp meter, as our charge on that dipole. So each one of these we have plus 10 amps times meters here. We have minus 10 amps times meters there. Okay, so again, this is useful for calculating the forces because the forces are going to not be determined by the field, and we'll find this in the next lecture or two. Not necessarily by the field, but in the change in the field, because obviously if you have a dipole, right? You remember this from electricity. The field will only push or pull these things. If the field pushes this guy this way, it's going to pull this guy that way, and that's going to cancel out. Now, that'll make a torque, which will cause this to start spinning, but it will also leave the thing spinning in the same spot that it was, or it won't accelerate it. So if it was already moving, it would keep moving, but this is physics, right? So that's more or less what we do for this part. This is how we deal with magnetic moments, and eventually how we're going to deal with forces on magnetic moments. All right? Well, nice talking to you. I will see you again next time.